Welcome back to the Somatic Sleep Lab. Tonight's protocol focuses on neural oscillations, the rhythmic electrical language of your brain. Over the next 45 seconds, your screen will now slowly turn black. Use this time to adjust your environment. Dim the lights. Adjust your position. Ensure your spine is neutral. As the light fades, we begin to lower the baseline arousal of your sympathetic nervous system. The lab is now dark. Understand that your brain never truly turns off. It simply changes its frequency. Right now, your brain is likely oscillating in the beta or alpha range, frequencies associated with wakefulness and light relaxation. To initiate deep recovery, we must transition your neural circuitry into the theta and eventually the delta range. This is not a matter of willpower. It is a matter of physics and the synchronization of billions of neurons firing in unison. Consider the thalamus. Located deep within the center of your brain, the thalamus acts as the grand central station, or the relay center for almost all sensory information. During your waking hours, the thalamus is wide open, allowing a constant stream of external data to reach your cerebral cortex. However, as we begin this protocol, your thalamus is beginning to gate this information. It is closing the doors to the outside world, allowing your internal systems to take priority. This gating process is driven by sleep spindles. These are sudden bursts of oscillatory brain activity that occur during stage 2 sleep. Visualize these spindles as internal shields, protecting your brain from being woken by external sounds or temperature shifts. Every spindle is a sign that your thalamus is successfully isolating your consciousness for the repair work ahead. As you breathe deeply, we move into the mechanics of delta waves. These are the slowest, highest amplitude brain waves, oscillating between 0.5 and 4 Hertz. During delta sleep, your brain undergoes synaptic scaling. Throughout the day, as you interact with your environment, learning, reacting, forming memories, your neural connections strengthen through a process called synaptic potentiation. Each experience, each piece of information absorbed, causes specific synapses to grow stronger, more efficient at transmitting signals. This is how learning occurs at the cellular level. However, this strengthening comes at a cost. By the end of your waking hours, many of your synapses have reached a state of maximum potentiation. They are operating at peak capacity, consuming disproportionate amounts of energy. Your neurons are carrying what sleep researchers call synaptic weight, the cumulative strength of all connections. If left unchecked, this would lead to cellular exhaustion, inefficient energy metabolism, and a loss of the dynamic range necessary for new learning. Deep sleep provides the solution through synaptic downscaling. As your brain enters the slow wave phases of stage 3 sleep, the very oscillations you are now experiencing, those long, powerful delta waves, actively trigger a process of synaptic renormalization. Think of it as a biological reset. The slow waves moving through your cortex are not merely a byproduct of sleep. They are the mechanism itself. During this downscaling process, synaptic connections that were strengthened throughout the day are selectively weakened, but not erased. The brain is extraordinarily intelligent in this process. Connections that are functionally important, those repeatedly activated or those tagged by emotional salience, are largely preserved. Meanwhile, weaker, less relevant connections are scaled back more dramatically. This creates space, both metabolically and informationally, for new learning to occur tomorrow. The result is that when you wake, your neural circuits preserve the essential traces of yesterday's experiences, but they do so at a recalibrated, energetically sustainable baseline. Your brain becomes efficient again, ready to encode new information without the noise and saturation that would result from unregulated synaptic growth. This is why sleep is not optional for learning. It is the price we pay for neuroplasticity itself. Think of your brain's electrical activity as a vast ocean. During the day, the surface is choppy, with millions of small, chaotic waves. As we enter the neural oscillation protocol, these small waves begin to merge. They become long, slow, powerful swells that move through the entire cortex. This is neuronal synchronization. When your neurons fire in this unified rhythm, the brain is able to perform tasks that are impossible during wakefulness. One of these tasks is the regulation of growth hormone. The majority of your daily growth hormone release occurs during these slow wave oscillations. This hormone is the primary driver of physical repair, knitting together muscle fibers, regenerating skin cells, and reinforcing the integrity of your organs. Without the synchronization of delta waves, the body remains in a state of catabolic breakdown. By following this protocol, you are shifting into an anabolic state of pure restoration. Now, consider the K-complex. These are large single waves of electrical activity that help maintain sleep and aid in memory consolidation. Along with sleep spindles, K-complexes represent the brain's attempt to process the environment while remaining unconscious. The K-complex serves a dual function. First, it acts as a sentinel, evaluating external stimuli to determine whether they represent a threat requiring awakening or benign information that can be safely ignored. When a sound occurs during your sleep, a distant siren, a creaking floorboard, the K-complex evaluates it in real time. If the stimulus is deemed non-threatening, the K-complex generates a burst of inhibitory activity that actually deepens sleep, preventing unnecessary arousal. You are being protected by your own neural architecture. But the K-complex has a second, perhaps more profound function. It coordinates the transfer of information from temporary storage in the hippocampus to permanent storage in the neocortex. This is the essence of memory consolidation. During the day, your experiences are initially encoded in the hippocampus, a structure designed for rapid but temporary storage. These memories are fragile, vulnerable to interference and decay. During sleep, particularly during stage 2 and the transition into slow-wave sleep, the hippocampus begins replaying these experiences in compressed, high-speed bursts. This replay occurs during what researchers call sharp wave ripples. The K-complex synchronizes with these hippocampal replays, creating a coordinated dialogue between the hippocampus and the cortex. Each K-complex provides a temporal window, a moment of coordinated cortical activity during which the replayed memory pattern from the hippocampus can be received and integrated into the cortical network. The cortex, with its vast capacity for long-term storage, gradually takes ownership of these memories. With each sleep cycle, the memory trace becomes more stable, more resistant to forgetting, and more integrated with your existing knowledge. Research has shown that the density and quality of K-complexes directly correlate with memory performance the following day. Individuals who produce more K-complexes during sleep demonstrate superior retention of factual information, better consolidation of emotional experiences, and enhanced integration of new learning with prior knowledge. Your brain is currently auditing your day, deciding which memories to keep and which to discard. This is the informational sifting process. The coordination between K-complexes, sleep spindles, and slow waves creates a hierarchical system of memory processing. Spindles provide brief windows of heightened synaptic plasticity, moments when neural connections can be efficiently modified. K-complexes orchestrate the timing and direction of information flow, and slow waves provide the rhythmic backdrop that facilitates synaptic downscaling and homeostatic regulation. Together, these oscillations form a biological symphony of memory consolidation and neural maintenance. As the slow waves deepen, your cerebrospinal fluid begins its rhythmic pulse. As discussed in previous protocols, the glymphatic system is dependent on these neural oscillations. The slow rhythmic electrical pulses act as a pump, moving fluid through the brain tissue to clear out metabolic waste. Every slow wave is a literal wave of cleaning for your gray matter. You may feel a sensation of heaviness in your limbs. This is the result of the reticular activating system, the part of your brain responsible for arousal, quieting down. The electrical hum of your consciousness is being dialed back. The background noise of your worries and to-do lists is being filtered out by the Thalamic gate. Your heart rate is now synchronizing with your breath. Your blood pressure is reaching its lowest point of the 24-hour cycle. Your respiratory rate is becoming perfectly rhythmic. You are moving past the gateway of stage 1 and stage 2, and you are now descending into the profound depths of stage 3 slow wave sleep. The oscillations are slowing. The thalamus is gated. The synapses are scaling back to baseline. The master rhythm of the brain is now in control. The analytical mind is no longer required. The lab is dark. System recovery begins now.